Alright, so let's say we are watching the water level in like, I don't know, a bay rise and fall due to some waves or something. Okay, so what we're going to do is come up with an equation to model what we're seeing. So let's say between the very highest and the lowest that we're seeing is a distance of, I don't know, what does water do? Like 3 meters? I guess it depends on where you are. So let's say that that's the change we're seeing, a 3-meter difference in the highest to lowest level of water. So let's say the water level was high when we first started watching it, at its highest point. And let's say we watch for, over the course of 1 minute, the water level goes all the way down and all the way back up 10 times. Like so. So if this thing's fairly periodic, and we're trusting we can make a nice equation for it. But let's start with the graph of what's happening. So the height of the water, I'll say y over time. So we said it starts high up, right? It goes to some halfway point maybe, and then it goes down to, I should try and do this right. And it goes down to some level, and then back up again to a middle point, all the way back up to its height. Continues on like this, right? And so you may know what I'm going to do. It's a wave, right? Oh, it's just lovely. Okay, yeah, you do better. All right, so there's my wave. I want the equation, though. But looking at this thing, we can remember some facts about these wave graphs, right? The height it goes up to, or the magnitude of the downfall there, is the amplitude. The amplitude goes out in front of the equation. And this one is starting up at a value of, at a t-value of 0, I'm getting a y value of, maximum, and that is actually a cosine graph. Okay, cosine starts at the top, sine starts in the middle, like that. But this is the cosine one. Okay, so we know it starts at the top, so it's cosine. We know the amplitude goes there. And then on the inside, we have to put omega t. So omega, remember, that is angular frequency, which is 2 pi times the regular frequency. Just the frequency is, in hertz, or things per second. Things happening per second are the units of frequency. And you multiply that 2 pi, and you get angular frequency. All right. And another thing on the graph, just if you're curious, is from peak to peak, that is the period, which is a capital T for some reason, I guess because it has to do with time. And we have that period is equal to 1 over frequency, although we might not need that in this case. So the amplitude of our wave here is, well, I said it goes from the very lowest to very highest is 3 meters. Well, that's not the amplitude. Watch out, they'll try to trick you like this. That would be this entire distance, right? Wouldn't that be the 3 meters I'm talking about? So our amplitude is half of that, 1.5 meters. Okay, we agreed on cosine. And now we need to find the angular frequency. Well, I think I can figure out the linear frequency f. If you look up here, I know that in 1 minute it happened 10 times. And, well, frequency is just things per second. They changed the unit from that to hertz for some reason. I guess Hertz was a good guy. So our frequency is going to be 10 things per 1 minute, but I need it to be in hertz, or things per second. So I'm going to convert that in 1 minute. There are 60 seconds. Cancel out the minutes. And so 10 divided by 60 is, what is that? Something? 1/6, I'll say. So the frequency is 1/6 things per second, or hertz. And so that means that omega is 2 pi times 1 over 6. 2 and the 6 do something, and I end up with pi over 3. And the units on this, once you multiply in 2 pi, are radians per second. All right, so that's my omega. So plugging that in here, omega is pi over 3 times the t, just because that's what goes in our equation. This is an equation of y with respect to t, so we would have to have y and t in it, right? And there it is. There you have it. So we just observed a phenomenon and made a mathematical equation to model it. That's pretty much the definition of physics, actually. So good for us.